algorithm 64. Algorithm 64 is also known, or it was published as algorithm 64 quicksort. And so this was published in 1961, I believe. I checked about, on Google Scholar, I found some 28,000 papers with quicksort in their title. Sir Tony Hoare, who is our next speaker, invented it as part of, I think, a language translation project, if I remember correctly. But that's actually a small thing among the many things he did. He invented Hoare logic to argue about programs and prove them correct. He worked on concurrent processes and how to prove things. Sorry? Oh yeah, it's still working. And today he'll be telling us about geometry, logic, algebra, and how it relates to computer science. Sir Tony Hoare, we're very glad to have you here.
Thank you very much. I wish I could repay your applause by giving a lecture as good as the one that we've just heard, but the best is the best I can do, and you will, I hope, find some similarities between my career and that of John Hennessy, but they're different in other respects. Okay. Now, I have three theses: that the foundations of computer programming can be taught as an aid to practical programming throughout a degree in computing science, not as a separate course, but always as part of the practical course that will immediately apply what has been learnt in the theory. The program development environment for all practical classes should be based on the theory, but it's also very important to have a program development department of the kind that is widely available in industry now for professional programmers, and which helps in at least the testing of programs, and increasingly in other phases of the development of the program right up to delivery and beyond. And the final thing is that the initial level of math that's required to teach these courses is available in the high school, and from that I will quote from my own experience. So, a summary of what I'm going to talk about. The summary is already published in your blue book, so I will move over it quickly and start with a review of Boolean algebra. George Boole is clearly the author of Boolean algebra, and he had an interesting life. He was born into a poor family. His father was a cobbler, a shoemaker, who wasn't a very good businessman, and at the age of 12 he became the principal bread earner for his family. Within 4 or 5 years, when his father died, he was a headmaster of a small school, moved to a larger school, and then he was always interested in mathematics, and he read and studied mathematics independently, but in correspondence with the leading mathematicians of his day. And they were willing and happy to help him to make progress in much the same way as Augustus de Morgan helped Ada Lovelace in her logical and mathematical investigations. In investigation into the laws of thought in those days, it was psychology and philosophy that they were interested in, and he gave a mathematical model of intelligent reasoning.
Could you please speak up?
Could you make me speak up, please? Thank you. Unfortunately, I have caught a cold, and my voice is not what it usually is. I don't think I can remedy it very well myself, but I will try to do so. Because he had to earn his living from the age of 12 onwards, he never took very much in the way of examinations or had no formal qualifications in mathematics. But nevertheless, in 1848, I think it was, he was invited to join the new Queen's College at Cork as a professor of mathematics. Thank you very much. Ooh, that's better, is it? Is that better? Yes. Thank you for mentioning it. Oh, it feels lovely. Now, I was interested in George Boole before I myself was invited to be a professor at the Queen's University of Belfast, which is originally the Queen's College at Belfast, also founded by Queen Victoria in 1848. And my mathematical qualification was that I had studied mathematics until the age of 14, and had given up mathematics since then and studied it as a hobby, like Boole did. But we both share the property that we were appointed as professors into a faculty that we were not qualified to enter as a student. I think that reinforces David's story too. Now, so let's start off. I will start by giving you the first lecture perhaps of your computer science course, which is about Boolean logic, and give you an example of an introduction of the operator OR. The important thing is the algebra of the operator. It's associative, commutative, and idempotent. And, of course, its purpose is to be used to prove theorems. And I've quoted a theorem that may not be familiar to you, that OR distributes through itself. Did anybody know that law before I told you? Nobody? Wow. I mean, gosh. I'm not quite in the league of Michael Atiyah, but to prove in front of your eyes a law that none of you heard of before, I think I'm very happy to do so. So here's the proof. It's a very full proof and shows that the theorem depends on all three of the properties that I've postulated, which is slightly satisfying. Its novelty of the theorem is also satisfying, but the real reason why I've chosen to show it to you first is that it's actually useful. I needed it. Well, I said we would talk about geometry. Obviously, talking about geometry, the relevant geometry for Boolean algebra is Venn diagrams. And so here I've given you a picture of a Venn diagram. Now, comparison between two Boolean values and between many is given in the definition, which shows pictorially that the first operand of the less than or equal is contained in the second operand, and it's written as R equals P or R. So now, first theorem about the ordering operator, that P is an expansive operator, that if you disjoin something with P, you can only make it fuller, larger, expanded. And the proof is more or less a single line from the definition. that if you expand the definition, you get something which is immediately obvious by idempotence. Here I've suppressed the use, as mathematicians do, suppressed the use of the associative operator, and I'll do that again. And it's really what justifies having association as an axiom. It's the value of association that you don't have to use brackets. So that's my introduction to logic, to algebra. Move on to the deductive logic of propositions. Deductive logic goes back to an ancient Greek philosopher, Aristotle, who was, he studied in the academy of Plato and founded another academy which is called the Lyceum after Wolf, and he lectured and wrote lecture notes, where students wrote the lecture notes on a number of different subjects in different faculties of a modern university. But I'd like to single out two of his particular discoveries, of which he was, as far as we know, the originator. That is biology and logic. In all the other lectures he gave, he referred to other ancient Greek philosophers as the originator of ideas, some of which were worse than his own, of course. But for these two, he doesn't give any references, and so we have reason to believe that he invented them both. And they're not unconnected, because logic, his logic, was designed to be useful in predicting the consequences of his discoveries as a biologist. Nowadays we use advanced mathematics and computers to deduce the consequences of our theories and predict the results of our experiments. Aristotle used deductive logic for the same purpose. I expect you've all seen an Aristotelian syllogism, of which I've shown you a famous example at the top of this slide. The two statements above the line are called antecedents. Oh, I don't need to go through all this. You're mathematicians, aren't you? So the important thing is that if you already know the algebra, if you know what an algebraic proof is, you can use the algebra to prove the correctness of a deductive theorem, of a deduction rule, and then to use the rule, you only have to prove the antecedents first, and after you've done that, you can use the consequent anywhere subsequently in your proof. So let's try and prove a proof rule. It's called the proof by cases. First of all, assume the two antecedents, and then out of the air you pluck the idempotence axiom and apply it to R. Now we can use the antecedents as substitution rules to replace both R's by the two different right-hand sides, P or R or Q or R. And finally, we can use the distribution of R through OR to prove the theorem. And the conclusion follows by the definition of the ordering. Now, the purpose of the proof rule is to give you a strategy for constructing proofs. And that is, I think, very important also for a strategy of constructing programs. They're based on proof rules, as we'll see later, I hope. So now a few theorems about the proof. We want to prove some of the proof rules relating to the ordering relation. And perhaps many of you have memories of going through this little exercise of proving the proof rules. The nice thing in this case is not that each proof rule shown here, reflexivity, transitivity, antisymmetry, depend on all the axioms of the partial order. Each of all the axioms relating to its definition, but by one axiom each. So I will ask you to verify, if you wish, that those derived proof rules are valid. Well, there's a very important property in computer science called monotonicity, which is a rather horrible word, and I prefer to use the categorical term covariance. That when you make, if you know that two variables or expressions, P and Q, are relatively ordered, then you can substitute one of them for the other, and in many interesting contexts, and the result will be to obtain a result which preserves the ordering of the operands. So covariant or monotonic operator, when applied to an operand, preserves the ordering of the operands. Very important engineering principle, because when we replace a component in an engineering assembly by one which is better, then it cannot get worse. It can only get better itself. If you put a more reliable component in, your assembly will become more reliable. Not always true if the laws that you are using and the principle you're using in your design are incorrect. So the science has got to be right, but if everything's working as it normally does, then improving components will improve the product. Very important principle also in the development of computer programs and in their optimization. Optimize a small part of it, you won't make the whole thing worse. At least that's the principle. So now let's move on to a branch of logic which is not so widely studied. It is spatial and temporal logic, sometimes called modal logics. But ever since Aristotle, in fact, it has been studied by philosophers and logicians, and especially in the Middle Ages, where they hope to find in a modal logic a way of reconciling the great theological paradox of this simultaneous benevolence and omnipotence of the deity. I'm going to draw your attention to William of Occam, who was the author of the Occam's razor, which I've always used as my philosophical and mathematical goal, not to make unnecessary postulates about entities, and partly because William of Occam was a Franciscan friar and a scholar at Merton College, Oxford, and many years later, many centuries later, I was also a scholar at Merton College, Oxford, and I studied philosophy. It was at Merton that I pursued my studies of logic and in my spare time, and obtained my only degree from any university, an MA in philosophy from Oxford University. The point about a temporal and spatial logic are that they give you two more methods of composing compositions. If your propositions are describing something, then I think I'll probably go to the next slide here. The propositions describing actions occurring in a particular region of space during some interval of time. So if you'd like to think of a fairly large proposition, take a volume called A History of France, 1789 to 1815. This is, of course, split into two volumes, one of which go from 1789 to 1800 and one from 1800 to 1815. That split is a sequential composition split. The two volumes sitting next to each other on the shelves are sequentially composed because they relate to immediately adjacent intervals of time. And similarly, for a history of England during the same period, if you wish to spread your interest further over Europe, if you have a history of England over the same period in your library or on your shelf, then it's related to the history of France by being run concurrently. Everything that actually happens in one of the two subintervals. So I think this is more or less a repetition, but it's an important concept. So we can talk about P and Q in terms of their start times and their end times, and we can define P parallel Q, P concurrent with Q, or P while Q, by starting them both simultaneously and finishing them both simultaneously, and the actions are in each case are the disjoint union of the axioms in the two intervals. So the axioms, now that we have a special case of a proposition which says that nothing has happened, and we use it as the unit of our sequential and our concurrent composition. Both of these compositions are associative and they have the same unit. It's very unusual in algebra to find two operators with the same unit, but it has some consequences that are very important for our application to concurrency. So now we can prove a proof rule, sequential proof by cases, which gives you two antecedents which differ only in the first argument of the semicolon, P on one of them and P dashed on the other. And prove a simple theorem which is going to be useful by assuming the two antecedents, we can quite rapidly prove that the new proof rule is true. And here's a proof rule which relates to sequential composition alone, which uses the associativity of the operator as its primary key. Again, a simple substitution in what I've singled out in red leads to a conclusion which turns out by definition of the ordering operator to be equivalent to the consequence. I think I've been there. Well, there are various corollaries of this sequential composition. If I replace Q by do nothing, null, and then I get the second of these two lines. If I replace R by null, I get the third of them. So now a brief note on unifying theories of programming. It's very important to my central project because you won't be able to teach the theory to your class unless you teach them the same theory throughout the course. All the tools must be based on the same theory or they're going to be inconsistent, and the actual language that you teach doesn't matter. As long as it obeys the same laws and the same theory, or even it's very interesting to point out when they don't agree. At least you've got a theoretical framework in which you can find out in a very deep sense why two programming languages are different. So let me try to give you the two interpretations of the ordering relationship that I've been using in terms of programming. If P describes what happens from the start of R, we've got two sides of the equation. They have the same start, of course. And Q describes what happens from the end of P up to the end of R, then R correctly describes the whole of the proposition P semicolon Q, which holds throughout the interval R itself. Because the two intervals on both sides are the same, and P semicolon Q holds in one of them, so it must hold in the other. Alternatively, you can say, well, supposing R is a program and you want to execute it, then one of the ways you can do it is first to execute P, and then this is followed by Q. So now I'm going to define the Hoare triple as just this proposition that I've been describing here. Now when I look back at the proof rule for the semicolon, which I've just given you, and do an absolutely symbol by symbol translation using this definition, I get the Hoare rule for semicolon. It's a direct consequence of associativity. And the two corollaries are obtained from the two appear in my original article as the Hoare rules of consequence. And that was a shattering discovery to make in my more advanced years, shall I say, because it suggests that the Hoare logic is much more complicated than it really need be. The algebra from which I've deduced these axioms is a great deal shorter and a great deal simpler than the laws which are known as Hoare logic. So I tend to use the word Hoare to mean what I might call the old Hoare, before I came to the realization of this. And then I realized that that could be misunderstood, that I was now the old Hoare and the other one was my previous incarnation. No. Now I'm going to define using the second interpretation, to define Robin Milner's notation, by which he defines languages such as CCS. It says the superscripted notation says that if you want to execute R, then one of the ways of doing it is to execute Q first and then P. Now, when I substitute that definition for the same theorem, I get the Milner's law for the semicolon. It's not actually due to Milner, but it's what Milner would have written if he'd been interested in semicolon, which he wasn't. And the two corollaries are what Milner would quote as structural rules he would express them as equivalences. I've expressed them as orderings. So, we have two theories. Robin Miller was a great friend of mine, and we always regarded each other as scientific rivals, and we fought like anything about the theories that we were promoting at that time. In fact, we both collaborated on a 3-year and very expensive research grant to try to bring our theories together into a single unified theory, which was very necessary because you can't really sell to industry any theory on which the experts disagree. Because if you go into an engineer's office and sell them this marvelous idea, then they will ask you what you thought of the theory that the last person who came into his office said. And if you say, well, that's all rubbish, really, and he says, well, that's what they said about your theory. You go away and work something out and come back when you agree. And we never did come back. Now we have agreed, unfortunately too late for Robin, but I like to pay this as tribute to him. There are lots of other proofs of the consistency of a correctness logic with an operational semantics, but they occupy many thousands of pages of symbols, which, how are we doing? Maybe I could introduce you to the basic principle of concurrency. I need a new law which describes the principle that a concurrent program can be executed sequentially by interleaving, something which was well known since the days of Turing, but the proof of it was pretty difficult because it had to use interpretation using a Turing machine. If you make that into an axiom, firstly, Turing has shown it will actually be true, and secondly, it will be much simpler. I have a much simpler, well, it won't have a proof at all because it's an axiom. What have I done? Oh, first of all, I've got to introduce concurrency. Well, it's the same, it really has the same laws. It's obviously associative and has a unit, and it distributes through all. The new axiom that I need is called the interchange law in category theory and in my theory now. And it looks a little bit complicated. I think it's called the interchange law because it interchanges the symbols which appear in the formula, the semicolon and the parallel bars. So let's have a look at it again. I've used coloring, trying to deduce some of the consequences of the interchange law. We can prove that the sequential composition is stronger or contained in the parallel composition. If we start with P parallel Q dashed, we can execute those P in the order P Q dashed or Q. That's what seems to be a misprint. P dashed. Thank you. I hope you can see what I mean. I think it's obscured by a misprint. Anyway, the point is we can now use the law of proof by cases to establish that a non-deterministic choice, the or between P semicolon Q and Q semicolon P, is one of the ways of implementing P parallel to Q. So for sequences of less than 2 operands, I have proved that and if I interpret the ordering as a refinement ordering can be implemented as, then I've proved the principle of concurrency in this very simple case. The a general case, here I've listed the 4 different ways of executing programs with 3 operands, and here I've speeded it up to deal with 4 operands. In the end, you get an interleaving of the red operand and the black operand, but within each operand, you can extract back just an interleaving, and we can take the red cards out and the black cards out, and they will be so the interleaving operator on the first line is really a shuffle operator. It's often called a shuffle operator because it satisfies this property. So I think how are we doing? Do I have 5 minutes? Thank you. Then I can go quickly through the interchange rule. From the statement of the interchange law, I can do a simple proof of an appropriate rule of reasoning, which I've displayed on this slide. It shows that the conclusion says that if you've got to implement a concurrent composition, you may implement it as a sequential composition in which you've taken one operand, either a dashed pair of operands or the undashed pair, and run them separately, which describes the calculation of the R parallel R dashed into 2 phases, one in which you run P and Q concurrently until they each reach their, let's try this on the, nope. I've pressed the wrong thing. I decided R is implemented by P semicolon Q, and on the right-hand side, I will start by executing P in parallel with P dashed, as shown here, up to a point at which the R reaches this semicolon, and the point in which R dash reaches this semicolon. And those 2 semicolons, as it were, are synchronized, and then synchronized at that point there in the answer, and the remainder that still remains to be executed is the parallel composition of P dashed and Q dashed. So, summarizing, we've got, when we translate these laws according to the same definitions that I've given for the ordering previously, we get a law which was rediscovered by, which was discovered by Peter O'Hearn in his separation logic, which is one of the most effective ways of dealing in a rigorous way with concurrency. We get which is expressed as in Hoare logic, and then we also get an operational semantics, a law which Milner postulated as defining the sequential composition in his language CCS. And they're both equivalent to the concurrency rule, which was proved directly from the algebraic axioms. So, algebra. I think algebra is wonderful. It's so much simpler. You read my little eulogy of algebra. But it's also so useful, because algebra is what is used in any correct transformation of a program while preserving its semantics. So all optimizations are dependent on applications of algebraic inequations, algebraic orderings, refinements. If you want to preserve the semantics, you can apply algebra in compilation to translate from one language to another, optimization, refactorization of code, obfuscation of code, and automatic generation of program code. And all of these things can be set as exercises to your first-year students. Optimize this formula. Unification of theories is really very similar to the unification of arithmetic that is provided in the foundations of mathematics. The mathematical models that are given in the foundations of mathematics uses sets and pairs and sequences, and every kind of number has a very different modeling structure, but the algebraic laws which they bear are very similar. And this is what I mean by a unification of theories. Not absolute identities, but really understanding fundaments of what makes them what they are, how similar they are, and why they're so different. Now here are some deficiencies of the algebraic approach, and they explain why we need geometry as well to serve as a model for the algebra. So in another lecture, I have given a description of how geometry underlies the kind of geometry, finite geometry, that underlies the algebra that I've been describing in this lecture. And if you look back at the Heidelberg lecture in 2016, you'll see me giving that lecture. Anybody against algebra? Anybody? Thank you very much.
So we have time for one or two questions. And as a reminder, don't run away. There's supposed to be the picture happening.
If you don't ask a question, I will give you some other people's answers to this question.
Well, you told us the rather reasonable idea that if you improve one part of an operation, that it won't make the whole thing worse. But then you warned us that perhaps that idea might not be true if your theory was wrong. Could you give an example of when that might be untrue?
Yes, it seems to happen whenever I replace a tap in my home. Can you think of an example? Let's put it this way. When it does happen, you have to change your theory. It's like an experiment that has disproved your theory when the law of refinement is not monotonic. It's not a covariance. You don't want to make that mistake again, so you have to revise your theory. And I'm afraid I can't often think of a nice example. I will try.
One more question. Well, if there are no takers, thank you very much for this wonderful lecture.